All right, I think we're live. Welcome everybody. My name's Leland Curtis. I'm co-lead of Computational Design with SmithGroup. Today we'll be talking about the KCU Dental Facade design. And we'll be diving under the hood of our grasshopper script. Now, I want this to be pretty informal. The goal is to expose my personal approach to parametric modeling. So the things we're about to show here, I'm not saying this is the right way to do it. I'm just saying it's a way of doing it. And I think this is particularly interesting as we get to the end. We're going to dive into some daylighting analysis on this complex facade. The topic of our overall meeting today is what's coming next. And I think on the daylighting side, we did something pretty different that I think could become more common down the road. So we wanted to share it with all of you. So to begin, all right. So this is what we're going to be going through. So here is a complex facade, and you see now as it's changing in real time, the daylighting values are updating. Now, anyone who's run daylighting analysis knows that this is not actually possible. It shouldn't be. Daylighting analysis for a full daylight autonomy calc should take minutes, maybe even an hour, and especially for a complex facade like that. And yet we're seeing real-time feedback, which would enable the designer to play and discover. So not only how do we make the daylighting happen, but also just the parametric logic for that crazy script to build that facade. Let's dive into it. So first on the parametric modeling, our goal here, way that I often try to approach parametric modeling, the goal should not be to simply achieve what the designer set out to do. If you're doing that, all you're doing is essentially doing it the old way but faster, which is great, right? If you have a complicated facade or if you have a design option you want, it's awesome to be able to maybe build that more quickly. But if all you do is use a script once, you're missing out on the real power of parametric modeling from my perspective, because I think the power of a parametric model is in your ability to experiment and to play with it. So the way I approach parametric modeling, and I want to give a shout out first to the design team. So Bill and Darren as lead designers, and Sujin and Matt Nozick in our Chicago office also participated in the some of the parametric logic that I'll be showing you here. So it's a real team effort. Just want to make sure they get their due. So here's where we started. We had this SketchUp model that the design team was interested in, and they had a variety of different goals. And every time you start out a parametric model, we really want to understand what the intent is, right? What are the rules? What are the logics? What are the constraints? So that we can break all that down and then develop a grasshopper script for it. So looking at this western facade, we knew that it might be a little hard to see here, but the glazing was increasing in width as you go from one side to the other. There's a whole bunch of gradients happening here. So you have increasing glazing. At the same time, you have solid panels that are changing size. And they kind of imagine both of these gradients overlapping. At the same time, the fins that you see on the edge are changing in width as they go, from thin to deeper. At the same time, they're changing in rotation. So they have just all this stuff kind of coming together at once. And it looks really cool. But then you start to look a little bit closer, and you'll see that there was some awkwardness because these gradients don't just align nicely. They don't fit to, say, anything that's a buildable tolerance. There's awkwardness in the design. So in theory, you have gradients, it's easy to write out, but in practice, it's hard to get all those things to align. So the constraints that we had, we knew we needed the panels to be rational widths. You couldn't have like 18.637 inches, right? You needed something buildable. We also needed these solid and glass panels as the gradients come together, they were competing. And so we needed them to be rationalized. We needed them to somehow align with each other. And we'll understand that a little bit more as we go. Also, the way that the fins and the fin gradient and the panel gradient were not aligning. So you'll see that you might have a fin that's just showing up arbitrarily in the middle of a solid panel, or it'll show up awkwardly in the middle of a window. It wasn't aligned with any kind of rhyme or reason because you had essentially arbitrary gradients all being passed over top of each other. And then let's say we can even model this facade or build it. Well, how do all these design decisions affect the daylighting performance? So we wanted to understand all of that, and we thought that we could do that with a parametric model in order to build out all these constraints, capture them in the code, and then allow the design team to see what that means. Because it's easy to say, go make it work, and then a couple days later you'll come back with a option and you'll say that's not quite what I needed, or it doesn't quite work, and then you go back to it, right? And we wanted to get past this slow iterative process and allow the parametric model to act as a collaborative design environment. And critically, we wanted to inform the daylighting while this was happening so that we understood the performance of these decisions in addition to the aesthetics or the buildability concerns. So here is the whole script, not asking you to read what any of these nodes are, but what I wanted to point out here, I find this often as I'm working through the grasshopper models. I feel like 80 to 90% of it is building what I call the lattice, building the sketch outline, and then at the very end, as you see in this yellow section, you build all the geometry. So you spend all this time, you feel like you're getting nowhere, allowing all the design decisions to have an impact, and then suddenly the whole thing just appears. Which the first time going through this might be completely demoralizing, right? Because you think like, this is taking forever, I have nothing to show. And as a design lead, I think our designers expect linear progress, where we'd expect, okay, you're halfway through the time allotted, I expect to see half of it done. But as we're showing here, I might barely have the outline of my panelization completed, and you have nothing to look at. And then at the last second, boom, the whole facade is done, and it's fully parametric. And then at the end here, there's a section where we can visualize everything and then even analyze the geometry. So I just thought that was pretty interesting to break apart the rough sections. So let's get into what I mean by a lattice structure. So my next approach to building this structure, I knew that we had different gradients of things going across. And I knew before we moved any farther that I would need to have access to my raw resources, my basic inputs. So the fundamental building block of this is the facade surface itself. I don't care if it's a long skinny rectangle, a tall skinny rectangle, whatever in between. Thinking of this parametrically, I want this to work for any surface I may have. So if they come back and say, oh, I changed the orientation, no problem. I'll input a new surface. So take the base surface, and then when I say generate a lattice, I'm referring to the like the fundamental pieces of it. So this section of code right here, I'm taking any surface and I'm isolating out the bottom curve, the top curve, and I'm also getting key vectors. So that way I have a frame of reference. So no matter what orientation the surface is in, if I mean X, I mean normal to the surface, or Z would be normal, whatever I define. So I'm kind of defining my coordinate system relative to the surface. So that way I can ignore all of that. Because I want to have it all be parametric to this base surface. So first I have to build out or pull out all the component pieces I'll need to work with later. This might seem like a lot of extra work, but it's really useful down the road. And then if I want to update things, it's robust, right? I can just pipe in something else. So I isolate the key curves that I need, I isolate the key vectors, and also the planes themselves. Normal different planes that I can then use, as you'll see later, to do different things. So this is kind of a standard practice that I do. Just build out the basic lattice, the basic building blocks that define my surface. Alright, so one of the first things that we said we need to do, we want this to be buildable. And right off the bat, and this is shout out to Matt Nozick, I think a really simple trick. Building something that's rational, I hope that's the right word, something that's buildable, right? Avoiding the weird fractions. If we're doing gradients, which right off the bat, we're going to have some awkward measurements, right? Because it's a cool smooth gradient. Well, those are weird, continuous numbers. So a really simple trick to get past this. So first you take that entire bottom surface and we subdivide it into our minimum segments. So in this case we said it's going to be 3-inch distances, right? So I don't care if it's 42 feet and 3 inches. So long as it's in that 3-inch, that's going to give me some modules that are reasonable. So I create a giant list of points every 3 inches along this bottom curve. Now the next step is to define the louver locations. So looking that I had the solid and glass, and I mentioned that misalignment of the louver in the windows. So the first thought we had is, okay, the louvers create the most noticeable panelization along the facade. So it might make sense to ensure that all these solid and glass panels are aligned with the louver. Rather than trying to have the louver fit the glass panels, let's just make the louvers first and then we'll fit everything else to it. But these louvers need to fit to that 3-inch modularity that we mentioned. So what we do is we use this little, so under the 4, there's a little graph mapper component. This is just a grasshopper tool we use to create a sort of a continuous curve that you can manipulate to create that interesting gradient. and then we evaluate the curve along these different points. So I don't want to get too into the weeds of exactly how grasshopper works. Just trust me that that gradient of green points, where it goes from very closely spaced together to farther apart, you can generate that and manipulate that using that little component in number 4. So once you have all these points, and actually circled in red, I should point out on the screen, this component right here takes a series of links and it evaluates the curve at that length. So if I'm generating a series of links using that graph mapper component, I simply plug in those numbers between 0 and 1 into that component and it generates my points. So it's really one component that does all of this. Now the trick is, I don't want it to be any arbitrary point. I want them to be exactly a 3-inch point. So zooming in, that's the image on the right here. If green is the exact point that was measured, I want to find the closest point in my 3-inch segments and use that one instead. And to do that, there's a component called closest point. So all I do is plug in the list of red points, plug in my list of green points, and it spits out a list of black points. And these black points now become my louver points. So we're basically talking about 2 components. Evaluate curve and then closest points, and bam, you have rationalized points. So it's a nice little trick to get it discretized, and no one's going to notice this difference. We're talking less than 3 inches, right? But this trick is going to be repeated. So alright, let's take a step back. Now the red points are those louver positions that I'd mentioned. So forget about the 3 inches. So here I am building up this lattice. And in the logic, we want the solid and glass panels to align with our louvers. So all my possibilities, previously it was a 3-inch segment. Now my possibilities are the louvers themselves. And I now want to do the same process all over again, where I'm going to create this gradient across this, and I want to find the closest louver position to that gradient. And once again, if red are my possibilities and green are now where I'm choosing to place the start of the panel, it finds the closest point available. And this isn't perfect, right? Perfect would be whatever my perfect gradient is showing me, but that's not my goal. My goal is to rationalize all this so that it all aligns. So the exact same process with that evaluate curve and closest point, I'm able to identify the black point rather than the green point. And now you can see they're identified by this these little bars at the top. And right off the bat, it might not be perfect. Odds are it actually looked like crap. And I'll show you a video later. It really doesn't work well. But you shouldn't expect an arbitrary gradient to just work well. So what a parametric model allows you to do is play with it. So that little where it says 6A2, this curve mapper, I play with this and I fine-tune it just right until the gradient aligns with the possibilities so that it looks good, which is very different than just going in and drawing it. But again, I'm trying to get a smooth gradient to fit on top of some constraints. So now we've created the start point on my panels. We have to do it one more time because we now need to decide what's solid and what's glass. And I mentioned there's not only the louver gradient and the solid gradient, but also the width changing of the glass panels. So we do the whole thing again, and this time I'm trying to identify where the end of the panel would be. And so I do the same process, and I am choosing, as shown here, now all the green ones are going to be the end of the panel to identify where that should go. And in the end of the day, I end up generating the panels. And it goes from, I think highlighted here in pink would be the solid panels, the leftover would be the glass, and all of these are aligned with the louvers that I set up previously. And we went through that whole process, right? And I know you're staring at a whole bunch of points and a bunch of nonsense. And then, and only then, once we have all these points collected, then I just plug it into a surface with 4 points. So bam, all in one node, we've generated our surfaces. And then to create the glass from this, so if I have all my solid panels created, in order to make this more robust, and I'll keep using that word, what I mean by robust is less likely to break or get buggy, which is pretty much guaranteed to happen, right? Anyone who works in Grasshopper, things look great, and then somebody says, well, what if I were to tweak this? Boom, the whole thing blows up and it takes forever. So as you go through this, you'll learn there's certain best practices to make it more robust. There's certain things you can do that make it more likely to work more often, with more changes. So that way when a designer comes and says, that's cool, but what about this? Constant curveballs, a little tweak in the code won't break everything. It'll actually still continue to work, which is half the reason for building a careful and well-constructed lattice structure. All that code I was talking about in the background is so that it'll work more often. So for example, how should we create the glass panels? I could create them the same way I created the solid ones, by identifying all those points and building it out. But in this case, I said, you know what? Wherever those solid ones are, I want the rest to be glass. Because what if the solids went right up and there was no glass? I mean, I don't think I want that, but maybe that would happen. If I were defining things, I might end up creating a zero area surface, and maybe that would blow something up. Who knows? Things can happen. So a more robust way is to take that background surface and do a brep multiple split multiple to basically pull out whatever's left over. And there's 1,000 ways of doing things. I said this is my opinion. I hope someone looks and says that's stupid. Here's a better way. That's what this group's for, right? Let's share different techniques. So that's a technique that I chose. I feel like it's pretty robust. It's slow though. I'm doing a brep split. Works fine for one facade. If you had a full building, oh no, that's going to take a long time. That's going to slow it down. It's no longer going to be real time. That might be a killer for your whole script. We can spend another day talking about fast ways of building facades using single plane meshes and things like that so that it can be more real time. But in this case here, I knew it was one facade and I could afford to have more robust but slower solid cutters and solid type tools. Alright, so that's how we got to the panels. I know, all this work just to build a couple panels. Now we want to build the louvers. Now louvers are pretty easy because we defined them basically by points that we set up in one of the first steps. You make a straight line, and all you have to do to make this louver, because we're doing it simply with just a single plane, is to, actually I can show you up here, the upper right, that's highlighted here. This command right here is an extrude command, where I take a line and I give it a vector, and it will extrude along that vector. And bam, I have my my louver. Now we talked about what are these louvers, what kind of gradients were we playing with here. So we have the depth of the louver, which would be determined by the amplitude of that vector. And we also have the direction of that vector. Both of those are going to change. So if our extrusion here takes the same line, that's not going to change, but this time the vector will. And here I have an amplitude command where every vector has a different amplitude. And if you come down here, I have another one of these graph mappers with the remap thing where I'm controlling the minimum and the maximum depth. And I have one number per louver, and I can adjust the range, and it's going to spit in a list of depths that's going to align with my list of vectors. So there we go. We have control over the gradient of the depth. Now how do we control the rotation? Well, the rotation comes from how we actually build the vector. And in this case, I chose to take that plane. I mentioned we built the frames, they call them in Grasshopper, or the planes. I, right in the beginning, took my surface and built a whole bunch of different planes. It's so that I could do stuff like this really easily. So one of the planes that I created was essentially flat. As you can see here, it's the flat planes at the base of each of these louvers. Because then I could simply rotate them by a certain degree. And importantly, I could see it. So I personally like to use techniques where they're easy to check. Although I did just show you how to build surfaces with 4 points, that's actually a little bit harder to debug because you have to look at points everywhere and it's hard to understand. Whereas if you were to go with, say, an outline of a polyline, you could see it and then you could see where it might be going wrong. So in this case, it's a little bit more visual than using vectors. Vectors are hard in Grasshopper to visualize, but planes are easy to see. So in this case, if I know that the x vector shown in the red of my plane, if you can see that from afar, if I know that's where I want things to go, I could quickly look at this, and if it were turning a way I didn't expect, I could see it, I would know it, and I would be able to identify what was going wrong. And it's a pretty simple command up here, this plane rotate, where I simply input the degrees it's going to rotate. It'll rotate the plane, and then when I deconstruct it, I take that x vector from the plane, and that's now the vector I want. So couple basic commands where I take the original plane that I had, build one at every point, rotate it, and then take that vector and extrude, add an amplitude, and then extrude that line by that vector. So a couple little components. what did I want to say here? Oh, why there's probably a lot of different ways of generating this rotation. An approach that I take is thinking first, what is the designer going to tell me? Like, what's the decision being made? And we should try to build our models so that the parameters, right, this is a parametric model, the parameters should be in the language of the design team. So right off the bat, they said, you know what, I want to rotate my fins between 0 and 45 degrees. So right there's a hint. They're talking in degrees. So if I were to say have these in radians or percentages or some tangent function, you know, there's a lot of different ways you could get degrees. I wanted to make sure that the input was clear and understandable. The fins are going to go from 0 to 90 or 0 to 45. That's understandable. So the parametric model has to be built with those as inputs. And that's no small thing, because there's 1,000 ways to get that kind of information out of a model. So that's a good approach. Not only build a robust lattice structure, but also make sure that you've identified all the decisions that you need to make so that they're logical. Is that what I'm trying to say? They're clearly understandable. All right. All of that just to create a facade that, as you can see here, right, both the glass and the solid panels are increasing, but they're not actually increasing at the exact same width. For example, this isn't a fraction of like 1 to 1. People watching this video won't know what I'm pointing at. So on the far right here, this looks like it's a 50-50 split. But as you come down here, you notice that that's a 1 to 2 split. So there's there's lots going on in between these. And then if you look at the bottom, as we start to overlay the fins, you can see how this is now much more rationalized. Now, I'm not saying that this is the best solution. I actually personally don't think this looks as nice as what the architects came up originally. But it does meet the idea of fitting all these constraints. So what is possible? What would it look like if everything aligned? Because the first time we saw this, we said, well, just make it fit. And through this process, I was able to show, like, this is no small task just to make this align. And in fact, it's quite limiting. So I'm going to play this little video for you to show how ugly it could get. So here I am adjusting this, and you can see how it's kind of freaking out. Right, all those different pieces are moving. This is the gradients coming together. So we were looking at something that we played with to get close, but there are a lot of ways for this not to work out nicely. So if you're trying to figure this out manually, think of how long that would take. Because you try something and be like, nope, that gradient's terrible. Nope. It's really hard. But now that the system is built, we're able to play and find and discover where the different gradients might align to be something more closer to what you want. And as this is one version. If you see in that original script, there was a lot more in here. We ended up creating, I think, 5 or 6, maybe even 7 different approaches for aligning these gradients to get closer to what the design team wanted. And on each of them, it was a modification of the script. So that lattice structure I was talking about, switching a couple things here or there would give a very different feel and look. For example, these are all direct multiples of the louvers. The glass and solid starts or ends at a louver. That was the instruction. It felt a bit like static. The gradients weren't really that good. It didn't really give us what we wanted. And so the design team said, well, actually, I don't want it always to align. I want them always to start at a louver. So every solid panel will start at a louver. But maybe the glass can be a little more flexible. Can you try that? And we could. But we had to rebuild some stuff in order to make that happen, because it was a slightly different logic than we put in. So there's a lot of variations. And I think that's where we as computational designers need to be more comfortable with that spur of the moment, well, what about this kind of question? And we need to be able to build out a structure that is robust enough to be manipulated to deliver multiple design options. Because ideally, you predict it all ahead of time. That's the perfect model, where they say, well, what about this? And you say, I already thought of that. Bam. And it just changes. That's a dream scenario. And very often, we can do that. But sometimes they need something different, and you can modify slightly rather than rebuilding. And that gets very, very powerful, because then you get to reuse your code and you get to experiment and play. So once again, it's not about building the first thing that you thought of. It's about building a design system that allows a designer to explore, learn, play, discover something different. Because if you want to keep doing it the way you've always done it, the same designs over and over and over again, yeah, you don't need this stuff. But if you want to surprise yourself, this is a great platform to enable you or your team to maybe do something that they wouldn't have traditionally done. Because now you've automated the modeling, and now you can spend your time designing. Any questions about the parametric logic before we jump into the analysis side of things? Yeah.
You said that you made like 7 different approaches to this logic, to the script. So I'm just curious on like how much time that you and I don't know the other teammates spent on actually creating those until you got to a point where you thought this is okay, this is like finally presentable.
Yeah, good question. Just so for the recording, the question was, I'd mentioned that we'd built 7 or so different logics for how that go, and the question was, how long did it take to build out all of those? I would say that if it took, oh gosh, maybe 3 days or so to kind of work through the first round, 1 day of tweaking it to build 7 more, and that's, I think, about what we tend to find, where takes a bulk of the work to build it once the first time. Even just to wrap your head around what the heck you're trying to do takes a long time. And once you have the lattice kind of figured out, tweaking it, you can rip through a lot of options more quickly. Now, some of them might be a big new build that could take days, right? But if you're lucky, you can find one small section of the code to tweak it, and then that could be 5 minutes. I actually have a story where we had this twisting tower, and I had this design idea of having some lit panel coming off of one part of the panel. So as you rotate around the building, the panel kind of becomes visible. And I was really excited about it, and my boss came up. I was like, well, that's cool, but what if it was on the other side? We're talking like a 40-story tower with thousands of these things. I'm not like, oh my gosh, to remodel everything just to move it from one side to the other. But that logic in the grasshopper script is incredibly basic. It goes from, do I want the point to start this as 0 or 1, meaning which side of the panel? Because I built that in. I could have made it in the midpoint if I wanted. So all I did was boop, slide it over, and I was able to answer that question. And it repeated itself across the entire facade. So if you're lucky, some of those questions are very clear, and it allows you to make minor modifications. In our case here, there was a more fundamental within the, as I say, the lattice structure. There's some logic about how the constraints we built in that we just saw, where we were forcing it to align with the panels way upstream, and everything else had to flow. So as we changed that, it caused ripple effects downstream. So there are all these little things we had to do. So it was longer than I think other cases, because it was more fundamental. Ideally, if you can identify that lattice structure, like a panelization of a facade. If your design team says, all right, I'm going to panelize it in some way, and then all you're doing is tweaking around with the exact design of each panel, that's kind of easy, because that's constrained to just the panel design. If you can maintain the lattice structure, modifications of the actual geometry are easier. As we pointed out, 80% of it's building the lattice, 20% of it's going to be on the actual geometry. It depends on every script, of course. That's your question? Cool. Yeah, what's up? You're saying the width of the glass versus solid? Yeah, exactly. They looked at it and they were like, I don't like it. Something was kind of off. They wanted much larger glass than we had originally put together, and so we had to change the way that we were defining the panels. So, for example, if we were stuck to the louver width, as we got to very large louver widths, we had very few options, right? Because we were strictly keeping them to those few points. So we only had a couple points to choose from. And those results didn't look good. That's kind of what it came down to. It wasn't really what they wanted. So that logic, even though it sounded good, didn't work out in practice. And they looked at that and said, that's not going to work. So that's when we came to the idea of, okay, we're not going to hold the glass so strictly to those louver points, but we will keep the start of the solid panel. So basically half of our panel edges aligned with the louvers. So it made it look a lot cleaner and a lot less arbitrary, while still giving the flexibility. So it was a bit of a trade-off. That was one of the options that we chose. But yeah, it came from a straight, they looked at it and was like, no, something's not right. That was not our design intent. but at the same time being able to show this is what you asked for, and I know it's not right, but at least now we're all convinced that it's wrong. That's no small thing. That's a good thing for the design team to get to, because now let's move on. Let's try something else. Cool. Let me check time here. All right. We got to move into daylighting.